Alright, you guys, good morning. Here's a quick look at some things that you're going to tackle today. Find the sheet that says Pre-Calculus Solving, Factoring, and Division in Polynomials. If you need to pause this video to find it, go for it, or get it handed out, you do that. But first I'm going to just take a walk through some of this stuff so you can see what you're getting into, and I'm going to use this kind of as a guide of big ideas that you need to have tucked away. So this is polynomial long division in number 1. Sorry it's a little tiny from this distance, but just know I'm just giving you a general idea. You remember the long division piece, you're dividing by 3x plus 2. And underneath the house, in the garage there, you got that 3x cubed plus 5x squared plus 8x plus 7. That's the work you're going to do there. And then I can work out, again, we'll have a key, I shouldn't say again, I will have a key eventually for you to peek at, but today you're just going to get as far as you can doing that, and then chat with each other to see how you're doing, to see where that gets you. Use synthetic division in number 2 to do the same kind of thing. Remember, if x minus 3 is a factor, or it's asking if it is a factor. This one I kind of want to work out for a second. Remember, you put 3 in kind of the box in the upper left-hand corner. That's the thing you're dividing in. This is actually the root that you always place here, not the factor itself, which is x minus the root. And then you put the coefficients 2, -3, -5, -12. You can pause if you need to. Just shout out, hey, wait a second, because I'm going to talk a little fast. We're going to bring down that 2. 3 times 2 is 6. Add those together, we get 3. 3 times 3 is 9. Again, sorry for going so fast, but I wanted to get this out there for you. 3 times 4 is 12. And you'll notice that we get a remainder of 0. So we'd say, yes, it is a factor. One thing, the other way you can test if something is a factor, if it is a factor, that means that x minus 3 is a factor, that means 3 is a root, which means that if I put 3 into this original function here, so I take 3 and I plug it into this 2x cubed, wherever there's an x, minus 3x squared, minus 5x, put 3's in each of those places, and then minus 12, we're going to get out 0 when we're done. So that works when it's a factor. What about when it's not a factor, when it doesn't go in evenly? So I'm going to pick something here just at random that doesn't go in evenly, because we know 3 is a root, so I'm going to do something else. So don't mind this, I'm going to clear everything that's on here. Maybe not quite that much. Yeah, sorry about that, I erased a little bit too much. But what we're going to do is synthetic division. 3 worked. What if I put in 4? I'm hoping it's not a root, I'm making this up as I go. 2, -3, -5, and -12. Okay, we have accounted for all powers of x there. And then we get down 2, bring that down. 4 times 2 is 8, take away 3 is, add those together and get 5. 4 times 5 is 20. And 15, hope there's no errors. And 4 times 15, uh-oh, what do we end up, 60 now? Okay, so there it is. And then we add down, and this is, what, all of 48? Something like that. That's our remainder, the last part is. Oh, that didn't work out. So that is definitely not a factor. X minus 4 isn't a factor, therefore 4 is not a root. So that's what we just found out. But what we can do is there's this thing called the remainder factor theorem that you encounter a little bit later. One thing that's really neat is if it's not a factor, what we can do is actually put 4 into this original function here. So watch what I'm doing here. 2, I'm going to put 4 cubed, and minus 3 times 4 squared, minus 5 times 4. So those all, I'm just putting this factor. I know it doesn't going to give me 0 because it's not a factor. But what's interesting is what it does give me. It's not 0. Plug that in here. If you want to do it mentally, you sure can. Plug, 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 plug. I'm going to do a little mental math. 2 times 4 cubed. 4 times 4 is 16 times 4, 48. 2 of those. Take away 3 times 16. Maybe you pulled out your calculator and got, oh, 48. Weird. Interestingly enough is when you put that root, that non-root in, the one that got you a remainder of 48, if you put it back into the original function, you actually get out the remainder. So the cool thing is, if you find out that you've got this function f of x, and x minus c is not a root, is not a factor. Actually, well, it doesn't actually matter whether it is. If it is a factor, something funny happens. A factor, boom, like we just found out here. Then, this is the big fun one I'm going to put in bright blue. F of that same c gives you the remainder. Ta-da! And that's called the remainder factor theorem. really handy, because if you just want to get to that remainder right away, it kind of tells you, like, it's not a root, but it kind of tells you how far off it is, what's left over. Like, it's 48 away from being a root. And if we could just take 48 away from that number, man, it'd be a root. And that's really informative. That has a lot of application. Let your imagination run wild in computer programming, especially when you're always trying to correct and find quick ways to get to things. Long division to get a remainder, or do you want to just plug something into a function and find out what the remainder is? Gotta tell you, I'm going with the shorter route, and that's kind of the forefront of good programming, is finding shorter ways to do things. All right, let's go to the next page here if I can. Next page. I'm having trouble going to the next page. Oh, there we go. So that's done. Down at the bottom here it says find all the real zeros of the polynomial function. So real as opposed to imaginary. And real does include rational and irrational. So in this particular problem, you're supposed to find all the zeros as long as they don't have an I included, the square root of a -1. And the best way you can do that to start with is do that P and Q business. And you get your Q's here, and you get your P's here. And you want to make a list of all the factors here, plus or minus 1, plus or minus 5. I want to do that ratio. Here's P. Oh boy, there's going to be a long list. Plus or minus 1, plus or minus 2, plus or minus 3. Oops. And we got all kinds of stuff. Plus or minus 4 go into that one. Plus or minus 6, we got that one. Plus or minus 7. And then we just keep on going, dot, 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 dot. And you want to do the ratio of, now this looks backward here. Remember, Q goes with the leading coefficient, and P is with the constant at the end. That P over Q ratio, this is possible rationals. So these are the ones that can be written as fractions. These are possible roots. However, there can be real roots, and real roots are like, the square root of some number, or pi. Those are numbers that are called, those are real. And however, like pi is irrational. Square root of some number is irrational. Can't be written as a fraction. So that's the distinction there. So you want to go find out what that is. Once you find your rational root, these irrational roots are going to pop up from some kind of quadratic formula. Remember how we ran into that yesterday? So you're probably going to, or solving a quadratic, that's going to be where you find that. And other methods, you don't have to use the quadratic formula. Sometimes you factor or just set it equal to 0 and go. So just keep that in mind. And on the flip side here, find the zeros of the function. That one right there. Same stuff we've been doing. You want to do the P and Q business. And you want to find out your rational zeros. Suggestion on this one, number 6. Why don't you factor out an x first? 0 is one of your zeros, because you're left with 2x cubed plus 3x squared minus 14x minus 15. And then work with the leftovers on the inside. Always look for a common factor you can pull out, especially if it has to do with x. And last, this is a 10-minute video, my goal, and this is the end of it. It says, let 4i be a zero of this function. Find all the remaining zeros of the function. Oh, my Lanta. Why don't you guys leave this for tomorrow? But if you're feeling really brave, what happens is you can do synthetic division with imaginary numbers. So I'm going to write out this function. By the way, this is x to the 4th, x squared, and a constant. A lot of missing coefficients. So 1 for the x to the 4th, 0 for x cubed, 13 for x squared, 0 for x to the 1st, and then our negative 48. We can do synthetic division with imaginaries, and that's where we're going to kick off tomorrow. And if you're feeling really brave and want to try it, it's exactly as you think. Bring the 1 down. 4i times 1 is 4i. Add them together, I get 4i. And 4i times 4i, this is where you earn your big bucks. Do you remember what 4i times 4i makes? 4 times 4 is 16. I times I is I squared. And if you remember, I is the square root of negative 1. So I squared would just be negative 1. I'll let you finish that off, see if that gets you started. That'll be a really good challenge for you to take on prior to me coming back tomorrow. The big thing, though, down at the bottom of this particular sheet, and I'm sorry it's toward the bottom, I don't think I have another page here of making it clear, but it gives you these imaginary roots. Okay, these i's mean imaginary roots, non-real roots. Those happen, right? We ran into just one of those yesterday when the square root of a negative pops up. Well, they always come in pairs. Imaginary roots always come in pair. So that's the key to solving this one. If I say negative 3, I'm going to make this a little bit different color because I need to spice it up a little bit. Let's go with crazy wacky purple here. So we got negative 3 plus 2i. That's what they're giving us. Well, it has a mate. It comes with negative 3 minus 2i. Free of charge, even though it's not stated there, that is implied. So that's a pair. That's an imaginary pair. So if I've got that, I've also got, it says in there 5 minus I. Oh, no, that's not it. 5 plus I comes with it, free of charge. And then it says and 3. Well, 3 is a real root, and that one does not come in pairs, but the imaginary roots do. So is it possible to have a polynomial of degree 4 and have all these roots? Well, degree 4 means there's 4 roots. There's 4 roots. I should write it here. Let's put it on here. 4 roots. And that includes imaginary, all your reals and imaginary. 4 roots of any kind is what you can have at most. Okay, and every root, it's going to have a combination of real and imaginary. Well, I've got 1, 2, 3, 4 imaginary roots, and then you throw in this 3 as another root. This would require degree 5, and I don't got that. I don't have that. For some better grammar there. Require degree 5. Yeah, I get degree 4. So no, it's not possible. No way. Sorry, we got to 11 minutes, 10 seconds. Enjoy your day. Hope you're doing well. Email if you need anything.